All right, good morning, everyone. Welcome back to the second day of the workshop. So to kickstart our work program for today, we'll have Austen Lamacraft from Cambridge who will teach us about quantum circuits as many body dynamics. And this will be one part out of two lectures, one this morning and another tomorrow morning. So please.
Okay, great. Thanks, Wenwei. It's great to be here, and thanks to the organizers. People can hear me okay? Yeah, perfect. So it's Wenwei implied this is a pedagogical lecture, so it's an hour long, and it's going to be really an introduction to the idea of quantum circuits as many-body systems and as many-body dynamical systems. So if you've written a paper about quantum circuits, you're not going to learn anything from this talk. This is for everybody else. If this link should be working, if it's not, it'll be working later on today, where you'll be able to find these slides, which you'll be able to look through at your leisure. Okay, so it's there are two lectures. So this first lecture is completely introductory, as I said. So it's really what is a quantum circuit from the point of view of many body physics and many body dynamics. And so I'll spend probably roughly maybe a third or half the time describing that, and then we'll move on to sort of a discussion of the kinds of things we might be interested in as theorists in terms of quantifying the dynamics, particularly with respect to the dynamics of quantum information. And then this will be rather generic, without focusing on any particular kinds of circuits, apart from ones which have a notion of spatial locality. And then in the next lecture, I'll talk about a few special sorts of circuits. So this, again, is from a theoretical perspective where we can actually make some theoretical progress. So in general, this problem is intractable. It's a many-body quantum mechanics problem. But there are certain situations where we can restrict ourselves to particular classes of circuits and then make analytical progress. So the usual story in many-body physics. Okay, good. So that's the outline. And so let's just get into it. So this idea of a quantum circuit, it's a notion which has worked its way from, I guess, physics into electrical engineering, then probably into computer science, and then back to physics again. But what we're talking about in general is an operation, a way to describe operations on a quantum state, usually of several qubits. So those are spin 1/2 subsystems, each with a two-dimensional complex Hilbert space. And each of those qubits will have a 0 state and a 1 state, which defines what we call the computational basis. And then we're going to see sort of pictures, a lot of pictures in this lecture of this kind here, where you've got operations. Here's one operation F and one operation G. The first one is acting on the top 5 qubits. And then the next one is acting on the lower 7 qubits. And I'll come back exactly to what I mean by these operations shortly. And so by composing operations like this, you can build up a more complicated operation on the overall system of qubits. So if you look at Wikipedia, you might find this sort of picture like one of these sort of engineering kind of pictures of what you can do with a quantum circuit. And some very standard notations coming from quantum computing for the things you might do. So these various blocks. So we've got 3 states going in here. These various blocks represent different operations you could perform. So the sort of simplest one, probably conceptually, is this one marked H, which represents a unitary matrix which acts on a single qubit. So that's a 2x2 matrix acting on one of these qubits. The dials here are supposed to represent quantum measurements. And then the thing at the left, which connects the 2 qubits, is the first example of what's called a quantum gate. So this is a 2-qubit quantum gate. So this is, in particular, this notation is something called a C-not gate, but doesn't matter too much. So these are sort of pictures you will see if you sort of open up a quantum computing textbook. But for the point of view of this program, or why we're sort of what we're focused on this week and next, I like to think of these not so much as representations of quantum computation or something like that, but a kind of dynamical or many-body dynamical system, but in particular one which takes place in discrete time. So that sort of fits in with this, the periodic part of our title. So here, here we've gone to an extreme limit of periodic dynamics, where we just sample the system or act on the system at discrete moments in time and propagate forward. And as you as you go from systems which are continuous in space to discrete in space, continuous in time to discrete in time, different things come out, and you can learn different aspects of many body dynamics. So that's kind of like the main interest. To be frank, the main reason people are building and interested in these systems is because of quantum computation, and I think. Probably for lots of us, all the many body things we're learning about many body physics are kind of a free benefit we're getting from this activity. And so from the quantum computation side, the purpose of these circuits is to generate an arbitrary quantum state by composing many simple operations. And that's just one way of doing quantum computation. There are others, including measurement-based computation and so on. But one of the reasons it's so fun to work on these kind of problems is they really do exist. Companies like Google, IBM, and a whole bunch of quantum computing startups are actually building platforms for quantum computation based upon gates, based upon circuits. The slightly dirty secret is they're not very useful at the moment. But what they are useful for is for making large, complicated many-body states, and that's very interesting / useful for people like us, I would say. So there's not a lot of quantum computation per se going on in this field, but there is a lot of what you might call quantum simulation or of a kind. Okay, so this is kind of my interest, and maybe it coincides with the interests of people here. So mostly I'm going to be talking about circuits where the operations we're performing are unitary transformations. So we'll sometimes, unitary operators, and we'll often use the term unitary gates. And what that means is that we take a subset of the qubits in the system and we act on them with an n-qubit unitary matrix. And we don't normally think of that as a if it's acting on n qubits, we don't normally think of it as a 2 to the n by 2 to the n matrix. We actually think of it as a multi-index quantity with n indices, n row indices for the n incoming qubits and n column indices for the outgoing qubits, where the indices just go over 0 or 1. Okay. So with that understood, when I say that these are unitary, it means that these tensors, or these multi-index quantities, satisfy a relation like this. So usual u dagger is equal to 1, but now we have to sum over all of these indices. So you can see very quickly that this whole subject descends into a sort of a nightmare of indices and index contractions. And one of the things we'll do in in these 2 lectures is to emphasize that thinking about things graphically in terms of what are called tensor network diagrams is a much more productive and way to go. And in fact, it's actually sometimes all you need to do calculations of quite non-trivial quantities. Okay, so as you know, if it hasn't become clearer, it will become clear very soon that everything in this game is a tensor of one form or another. So if we've got a state of n qubits, you could represent that as a 2 to the n dimensional vector, but it's much more sensible to think about this computational basis of n qubits and label each of the amplitudes in that computational basis psi by n indices, which can take values 0 or 1. And so we write the overall state like this. And quite a, to avoid these big, long indices, I often use this shorthand notation of S1 colon n. This is MATLAB or Julia style notation for these multi-index quantities. Okay, so if we act on n qubits, then we're dealing with operators which have matrix elements which are obtained by sandwiching between these computational states. And so that's represented by a quantity which has got n row indices and n column indices. Okay, so we don't want to really spend a lot of time writing down these enormous tensors explicitly. So what we're going to use is this graphical notation, which some people will have seen before. The idea is extremely simple. A tensor is denoted by a blob. It could be any kind of shape you like, it's fine. It could be a square, it could be a circle. And you add one leg to that blob for each of the indices that the tensor has. So if it's a vector, it just has one index. If it's a matrix, it has two indices. If it's rank 3, it's got 3 indices and so on. And then the second crucial rule is that if you wanted to perform a contraction by summing over a shared index between two tensors, you denote that just by connecting their legs together. So here we've got some very simple examples of that. So on the bottom or left here, we've got matrix multiplication as it looks in this language. So we've got two blobs, each with 2 legs, and we are connecting the middle leg here, which is denoted by J, and that indicates we sum over that leg. And so the expression at the bottom is exactly the same thing as the thing at the top. So this is not just a sort of cartoon language, it really is a representation of exactly these mathematical expressions. I mean, it has to be said that things are never quite that simple, because obviously one has to, if I draw a circle with some legs coming out of it, I have to really explicitly, sometimes I have to really explicitly label the legs so you know which ones are doing the contraction. But normally it's quite clear, and when it isn't, then you can add some additional labels, as in this picture. Something more complicated, we've got 3 rank 3 objects A, B, C, with some more complicated pattern of contraction, which involves these 3 summations over L and N, which is denoted by this. Okay, so in this way you can build up extremely, or we have to build up extremely complicated patterns of contraction, and the graphical notation is the way to do it. There's a very nice tutorial if you'd like to actually learn about some of the computational aspects of this. Glenn Evenbley has a very nice tutorial site with lots of code examples, which is where I took these pictures from. This link, which will work on the slides as you view them in your browser, will take you there. Okay, so let's look at some simple examples. 1 qubit, very simple. It's a unitary matrix acting 2 by 2 unitary matrix acting on a single spin 1/2 state. So simplest case is multiply by a Pauli matrix, X, Y, or Z. So I'll use this quantum computing notation rather than the sigma matrices. In general unitary matrix acting on acting on a single qubit can be written in terms of 4 parameters satisfying this normalization constraint. And often in quantum computing applications, you don't have to deal with these very general forms. You just deal with a restricted discrete set. One of them we already saw on that earlier figure. It was called the Hadamard gate, which has this form here. It's a little bit like a baby version of the Fourier transform. Okay, so that's one qubit, and then 2 qubits where conventionally you need to choose a basis, and the conventional one is 0, 0, 0, 1, 1, 0, 1, 1. So we have our 4 states, and so our gates now are represented by 4 by 4 matrices, and obviously things are more complicated, but some simple examples. This one's called the swap gate. It just exchanges the qubits on site 0 and 1, or if you like, exchanges the state. So if I act on state 1, 0 with a swap gate, I get 0, 1. So again, extremely simple. This has the feature, you'll notice that it takes product states to product states. Okay. Something slightly more complicated, we can take the square root of that matrix, which is imaginatively denoted square root of swap, and that has this form. So slightly more complicated, but the one thing to point out about this is this one takes a product state to a non-product state. Okay, so it generates entanglement. We'll talk about exactly what I mean by that more precisely. But for the moment, think of it as just generating a non-product state from a product state. So that's different from what the swap gate was doing. Some other things about this, you can observe that despite this additional complexity, it still conserves the number of 1s and 0s. So if it acts on 1, 1, it takes us just to 1, 1, 0, 0 goes to 0, 0. The importance of this one actually is that together with an arbitrary single qubit, this forms a universal single qubit unitary operator. So this is what's called a universal gate set, which can perform universal quantum computation. As far as that means it can just generate any kind of unitary transformation. This was used in Wenwei's talk yesterday. Okay, so that was some simple examples of 2 qubit unitaries. In the general case, this is going to be some 4 by 4 unitary matrix, and I don't know how helpful it is to put this is the explicit parameterization of the 16 parameters. So actually, we might use this a little bit more in the next lecture. So in this expression, we've got these lowercase v's and u's represent 1 qubit unitaries, which act before and after this 2 qubit unitary v in the middle there, which is parameterized by 3 parameters jx, jy, jz. So this is the explicit form. Sorry, it's slightly cut off here. Anyway, this is rapidly you start dealing with very large numbers of parameters, and there's a lot of freedom to choose what kind of dynamics you get. So now let's start thinking about this as a kind of dynamical problem. So we could regard these unitaries acting on a bunch of qubits as arising from time evolution. That's the first, the way in which we encounter this when we learn quantum mechanics for the first time. So in other words, we regard it as the exponential of some Hamiltonian. What kinds of Hamiltonians do we meet in sort of many qubit systems? Well, the very simplest case would be a Hamiltonian, which is a sum of operators which just act on each qubit separately. And if we do that, if we have this situation, then things are very simple, of course, because when you exponentiate this operator, it factors into an exponential which is acting on each of the qubits separately. And so things are rather simple. Okay, but this isn't going to get us anything particularly interesting. What we really need to do is to have at least 2 qubit operations going on. The simplest example is what's called the exchange Hamiltonian, which is this one up here. And here, this is composed of Pauli x, y's, and z's, which are acting on the 2 qubits. And so I've written it on sort of on the left-hand side in a kind of long form notation in terms of tensor products. On the right-hand side is how most physicists will normally write this. They will use subscripts to denote which of the 2 qubits you're acting on. So x sub 1, x sub 2. Now, it's sort of a fun exercise to convince yourself that this exchange Hamiltonian operator is basically the same thing as a swap operator, or rather it's 2 times a swap operator minus 1. So you can do this in various ways. I mean, the most straightforward way is just to write it out in terms of tensor products of Pauli matrices and then compare it with the swap operator that I wrote down before. So if I exponentiate this operator, then I get something which, apart from some overall phase, can be written in terms as a linear combination of the identity operator and the swap operator with the coefficients which appear in that combination depending on this coupling J. And if we take some special cases, so if we set the J equal to pi over 4, we get the swap gate. If we set it to pi over 8, we get the square root of the swap gate. And in general, we have this 1 parameter family of gates, which are all rotationally invariant, in fact. So when I said earlier that the swap and the square root of swap, they conserved the numbers of 0s and 1s, they actually have a higher symmetry than that. They're fully rotationally symmetric. Okay, so if we think about what would happen if we took a Hamiltonian consisting of operators which acted on pairs of qubits and we exponentiated that, then things turn out, are more complicated. And the reason for that is that if you act on a pair of qubits, then the operator which acts on I and j qubits is not going to commute in general with the operator which acts on j and k qubits. Okay? So it's not going to be the case that if I exponentiate this sum, it can be factored into a product of operators which act on pairs of qubits. So sort of pictorially, what's going on like this, what's going on is this here. Each of these little h's is acting on 2 spins, but they overlap in some way. So we need to think a bit harder about how to deal with the unitary which you get when you exponentiate this kind of Hamiltonian. And one way to do it is via what's called the Suzuki-Trotter expansion. So the idea here is to decompose the Hamiltonian into 2 parts. And then instead of, well, it's sort of cheating somewhat, instead of just exponentiating in one go, you exponentiate with a small exponent, HB, and then HA, and then HB again, and then HA, And you alternate these two things until you've got the exponent you want. And the advantage of doing this is, although HA and HB don't commute with each other in general, the failure to commute is only a small problem, is that you only make a small error when you divide the exponent by 1/n. And so in the limit that n goes to 0, this procedure is exact. And when n is finite but small, you can make some controlled expansion. Okay, so it's not exact, but it's a way of dealing with this. So now, what does this look like? What if we because obviously this is completely general of just splitting a Hamiltonian into two pieces which don't commute. What does this look like if we apply this to a system of qubits where the individual 2-qubit Hamiltonians act on neighboring sites? So a natural way to split up the Hamiltonian is into a piece HA, which acts on site 2J and 2J plus 1, and then a piece HB, which acts on 2J minus 1 and 2J. So in other words, we sort of have two, we have two interleaving sets of bonds, and we act on them separately. So when you exponentiate HA and HB with some small exponent, we can now think of representing those exponents as one row of this circuit here. So let's say this was the result of exponentiating HA, and then this was a result of exponentiating HB. And then the overall operator we get when we take the nth power of this is represented by this large quantum circuit, which has this nice regular structure to it. So this is one of the ways in which what I'm talking about today is specializing the sort of general case of quantum circuits. It has a particular kind of spatial and temporal structure to it, which is characterized by this brickwork pattern. So we'll be sort of talking about circuits with this pattern from now on. So just in terms of some terminology, I'll frequently talk about space. I mean the horizontal direction along here, and when I talk about time, I mean the vertical direction. That seems to be a habit of convention that we've got into in the many body physics side of things. Unfortunately, it's the opposite of what the people in quantum information do, which is rotated by 90 degrees, but we just have to live with that, I think. Okay, so this is space, this is time as far as we're concerned, time running upwards from the bottom. Okay, so this is one way in which this kind of quantum circuit can arise from the exponentiating the Hamiltonian of some two-body Hamiltonian where the individual terms act on neighboring sites, and then using the Suzuki-Trotter decomposition. There's another way in which it can arise. Maybe it's more in keeping with the theme of this conference, and that's when we deal with time-dependent flow case systems, in particular stroboscopic systems. So this would be where the time dependence is rather simple. It contains a static Hamiltonian, and it has some kick, which operates at regular intervals in time. So in this case, integer intervals in time. And so a particular example that which we'll come back to quite frequently in these lectures is called the kicked-Ising model, where the constant part of the Hamiltonian, I mean, actually various ways of presenting this, but in this case, the constant part of the Hamiltonian is a regular Ising model written in terms of the Z Pauli operators, where we have some coupling between nearest neighbor Pauli's ZZ coupling with some coupling J, and then we have a field in the Z direction H sub J, and that part, of course, all the terms there commute with each other because they're all written in terms of Zs, and then this kick, which happens at integer time intervals, is a transverse field which is acting in the X direction. Okay, so this looks relatively complicated. And if you were to write down the usual expression for the evolution operator as a time-ordered exponent, you might think that was a, in the general flow K case, this is a rather fearsome thing to try and understand. But in this stroboscopic case where you have kicks, things actually simplify in a very nice way. And that's because when we're not being kicked, so when we're not any time other than an integer time, we've just got the first part of the Hamiltonian, and we can exponentiate that Ising Hamiltonian rather straightforwardly because it's diagonal in the computational basis. And then when a kick happens, the kick completely dwarfs the Ising part of the Hamiltonian, and we just have a transverse field acting. And that's rather simple to understand as well, because that really is just a single spin, a single qubit Hamiltonian. It's a sum of xj terms. And so we can work out the unitary transformation corresponding to that term separately. And all that happens in this kind of evolution is that you interleave these two kinds of time evolution, one, the exponent of the Ising Hamiltonian, and one, the exponent of the transverse field. So, this is what it looks like down here. Our unitary operation, our unitary time evolution after n steps is given by the nth power of a single step, and the single step involves this exponentiation of the Ising Hamiltonian acting followed by the exponentiation of the kick. Okay, good. So it's simple to write down. It's still not clear exactly what kind of evolution you get. Now, one nice thing about this, if you stare at it for a little while, and it's not immediately obvious, but you can put this kicked Ising model, this flow K problem, in the form of one of these brickwork circuits that I just introduced. So that means you take this unit that I'm drawing on the board here, and you imagine making a brickwork pattern out of it. And when you do that, you can probably see that you begin to form a layer of these I blocks, which represent the Ising coupling, and then you have a layer of these K blocks, which act on single qubits and represent the kick, and then you have another layer of these Ising couplings here. And the only slight subtlety there is this factor of 1/2, which arises because when you make this layer of Ising couplings, they overlap. And so you divide the field which acts at in each circuit, in each gate by a factor of 2. Okay, so in this case we saw how those brickwork circuits arose from sort of the Suzuki-Trotter decomposition, and now we've seen how the same thing can arise in a stroboscopic flow K problem. And so this brickwork pattern captures a important feature of locality, and that is, it seems to be a kind of baked into a lot of the platforms that people are building for quantum computation. So this is a view of the Google Sycamore processor. It's a schematic view on the left and the actual kind of glossy publicity shot on the right. And this is a two-dimensional layout. So this is two dimensions of space. So far, I've just considered one dimension of space and one of time going vertically. But apart from that, you can see that the qubits, which are denoted by these crosses here, are coupled to each other in a local way. And we'll see that this locality plays a very important role in the dynamics of these circuits. Okay, so just something quickly about how hard it is to do calculations. In general, we expect many body quantum mechanics to be sort of exponentially difficult. And that's because the state we're dealing with, if we've got n qubits, is 2 to the n dimensional vector. And if we're going to update that state, we have to act on it with a unitary matrix. And if in the sort of most naive approach would be, so I'm acting on this big vector with a unitary matrix, it's going to take me order dimension squared time to make that operation, so 2 to the 2n. In fact, the matrices which correspond to gates are sparse, and therefore it would actually only be 2 to the n, or order of the dimension of the problem. But this is still exponentially large, right? So as soon as you get a large number of qubits, you begin to run into this exponential explosion in the difficulty of the problem. And this is the thing which is behind the whole idea of quantum supremacy or quantum advantage. Really, you try and set people the task of doing some difficult but useless computation, which can be thought of as which can be represented by a quantum circuit. So in particular, what's done in these circuit sampling demonstrations of quantum supremacy, which is what Google claimed a few years ago, is to start from a particular state, apply some complicated set of gates, and spit out some very complicated multi-qubit state, and then just to measure it. So you measure whether it's 0 or 1, and you make an empirical, you work out the empirical distribution of bit strings which come out of that measurement. And then you try and you sort of hand that as a challenge to somebody with a classical computer and say, can you compute this probability distribution that came out of this circuit? It doesn't, there's no particular reason to focus on one circuit rather than another. I mean, these are in fact chosen randomly, the gates, to perform this computation. And so the point is that it is difficult, but in the years since Google made this claim that even the largest supercomputer would not be able to make this calculation on the same timescale, there's been actually a very nice back and forth between people who develop numerical methods and the quantum computing people, leading to sort of optimizations of memory on supercomputers, followed by improved tensor network methods, and there's some references here. And so it's all been rather sort of kind of a fun competition. But I think most people would say that it's not completely clear that quantum supremacy in the initial sense is here yet. Let's leave that aside. I mean, this is, of course, one of the reasons a lot of people are excited about it. But let's return to thinking about dynamics problems and what are the kind of quantities of interest. So the very simplest thing you could ask about is an expectation value. So in other words, I take some operator, I start from some initial state, I apply this circuit, end up with some state, capital psi, and then calculate the expectation value of an operator. And so obviously that has the mathematical representation so I can think of this in two ways, right? Well, I can think of evolving my state psi naught by this unitary operator acting on it, described by the circuit, and then calculating the expectation value. Alternatively, I could think of Heisenberg evolution of this operator O, given by U dagger OU, and then taking the expectation in the initial state. I'll try and stick to this notation of using a curly U to denote the overall circuit and the usual uppercase U to denote the gates. Okay. So the simplest thing we could imagine doing is calculating the expectation value of a single qubit operator, having applied the circuit to it. And we're going to represent this graphically. And to do that, we always have to deal with the fact that, as we've seen just on the previous slide, you always have U daggers to go with, you always have U's and U daggers to deal with, and we have to distinguish them in our graphical notation. And so, with apologies to people with red-blue color blindness, I'll use this notation. I'll try and flag it up as I go along. So the blue gate on the left is our original U, and the red gate on the right is U dagger. Okay, and these are two qubit gates, so they've got two legs coming in, two legs coming out. So unitarity of these gates, U dagger is equal to the identity matrix. If we write it out in components, it looks like this. And now if we express this in terms of the graphical notation, yep. Yeah. Yes. The notch is just to tell you that in general, the four indices are different. There's no symmetry. Yeah, and so in a sense, it could be directionality in time, but also the left qubit's different from the right qubit. So unless we specify it in more, we should distinguish. We can't just flip it over and rotate it. So it's just, yeah, it doesn't play too much of a role, but that's the idea. Actually, it plays one important role on the next slide. Like that. Okay, so this unitarity condition here, now we're going to express it in our graphical language like this. So we contract the indices between our U and your U dagger. We could either do U dagger U or U dagger, and they're both equal to the identity matrix on two qubits, which is just a product of Kronecker deltas, which is represented by these two vertical lines here. Okay, so keep this condition in mind. We're going to be using this a lot. Okay, so this is much better than dealing with this condition at the top, written in usual notation. Okay, so how can we use unitarity? So let's think about this expectation value, calculating an expectation value. So the way to interpret this picture is at the bottom, we're feeding in some initial state. Let's leave it unspecified for the moment. Then we act with the lower half of this picture represents the blue unitary circuit made of our blue gates. And then we have our operator O, the black dot, that we're interested in evaluating its expectation value. And then the top half of the circuit with the red gates represents U dagger. Okay, and then and so this is what we want to calculate. And we can actually make things, you know, at the risk of sort of compressing our representations more and more, we can actually make things a little bit more simple, because every time, you know, for every red gate, there's a blue gate. And so we can fold the circuit on top of each other in what I will often call the folded representation, and represent these folded gates on top of each other by a purple gate. And you'll see that the notch has flipped from top to bottom because I folded it on top of each other. So this is the, you know, one place we're actually using this notch to be completely clear about what we mean. And so these purple gate now, the legs on this purple gate now represent 2 indices and therefore 4 dimensions each one. And the condition of unitarity where we contract the internal, the legs between the red and the blue are now represented by this picture at the bottom, where the circle here represents the contraction between the 2 indices which form a leg. Okay, and so I can either contract on the bottom, I'll get a Kronecker delta, or contract on the top. Okay, so in this folded representation, this is how unitarity looks. Okay, I'm sorry about this picture. Those blobs are now semicircles, but they mean the same thing. Okay, so this is in the folded picture. This is how our expectation looks, and our operator, the leg without a semicircle is where we're going to put our operator. And now, if we can apply this condition of unitarity, so if you can think how it looks, or if you click, you will actually be able to see what happens. So let me just go back. This is what we had before. We start applying unitarity, cut things away, and we end up left with this kind of wedge structure here. And I'll refer to this as a light cone. And so it really is reminiscent of the sort of causal restrictions we see in relativistic physics, but it emerges just from the unitarity condition together with the locality of the gates. Okay. Good, so that's how it looks like when we calculate a expectation value. And actually, one thing I should say about this is that it only, you know, we could have, imagine we started with a very wide gate, sorry, a wide circuit. By cutting away like this, we've actually seen that our operator at the top here only depends upon the part of the circuit which is contained inside this causal wedge. Okay. I seem to have lost clickability. Oh, I know why. That's because I clicked somewhere. Oh, okay, that's my fault. All right, good. If we want to go from an operator to a something more complicated, maybe an operator which extends over several sites or something like this, one way to think about that is in terms of the reduced density matrix of some region, which I'll call A. And so the idea is that the reduced density matrix in quantum mechanics is you trace over the rest of the system, which I'll call B. If you do that, it has a very similar kind of form here. Now I'm imagining that we're focusing on the reduced density matrix of the 4 sites at the top here. And if we apply the unitary condition again, then we cut away everything, all parts of the circuit apart from this wedge. And to determine the reduced density matrix at the top, all you need is this part, this remaining wedge of the circuit, together with the reduced density matrix of whatever goes in at the bottom, whatever initial state in the bottom. So everything else doesn't matter, just the bottom of this wedge and the circuit represented by this wedge. Okay, so what about entanglement? I mentioned that once or twice already. So the reduced density matrix we just introduced can be used to quantify entanglement between the subsystem A that we had in the middle there and the rest of the system. So a general state is a vector in the tensor product of the spaces describing A and B, and we can write a general state of that tensor product in terms of a set of coefficients sub AB like this, where A and B denote some basis states going over the dimensions of the 2 subsystems. So these, so A and B here it could be very, very high dimensional if we're dealing with two large subsystems. But we're going to regard these coefficients psi a, b just as a matrix and perform a singular value decomposition, which is just a basis change in those two subspaces. So once we've done that, we end up with an expression like this, where these sigmas, this is called a Schmidt decomposition, but it's really just the same as a singular value decomposition in linear algebra. And the sigmas here are called the Schmidt coefficients, but they're just the singular values of the singular value decomposition. And if now in general, these Schmidt coefficients really quantify the entanglement of the system. For example, if only one of them is non-zero, then we have product state. And depending on the values of all the others, we have different levels of entanglement. So in the case of a product state, we have no correlations in the system. And the next sort of non-trivial example, if you like, is what's called a Bell state, which many people will have met, where you just have your two subsystems are just two qubits, and you have a state like this. And this is already in the Schmidt decomposed form, and the two Schmidt coefficients are just 1/√2. So neither is larger than the other, so we're as far from a product state as we can be. And the relationship between the reduced density matrix that I was talking about and this Schmidt decomposition is very simple. If you compute the reduced density matrix, it's written in terms of the Schmidt coefficients and the basis states in the Schmidt decomposition. So the eigenvalues of the reduced density matrix are just sigma squared. And now those values represent the full, if you like, all the information you have about entanglement between subsystem A and subsystem B. You can quantify in various ways. The simplest way is the von Neumann entropy. So usual entropy familiar from statistical mechanics, which vanishes for a product state and is otherwise positive. But kind of a general set of quantities are the Rényi entropies characterized by some non-negative index alpha, which are basically related to the power sums of the eigenvalues of the reduced density matrix. So alpha goes to 1, corresponds to the von Neumann entropy, the entanglement entropy. Alpha goes to 0, just counts the number of non-zero Schmidt coefficients. Alpha equals 2 is, sorry, this is slightly mangled, this expression is related to the sum of Pn squared, which is just the purity of what's called the purity of a density matrix. Okay, so let's think about, in a very simple model, what this how entanglement behaves in circuits. And this is more or less like the simplest non-trivial circuit I could think of. It's just made of swap gates. So at each layer of the circuit, you just swap over 2 qubits. And you can see by applying that circuit many times, what happens is a qubit just either flies off to the left or it flies off to the right. But to make things a little bit more interesting, we can start from an initial state, which is not a product state, but a product of Bell states. So the fact that these two lines are connected at the bottom here is indicating that the initial state is a Bell state of the kind we just met. And the reduced density matrix of a Bell pair, if you trace over one of the components of the pair, is maximally entangled, as these two Schmidt coefficients equal to 1/√2, as we just saw, and therefore its reduced density matrix is 1/2 times the identity. And if you think about the entanglement entropy in that situation, we have, in the reduced density matrix, we have a factor of the identity whenever we've got one component of a pair inside with its partner outside. So if you have one part of a Bell pair ends up inside and the other one flies outside, we get a factor of the identity. If both parts of the pair stay inside, they give a pure state contribution to the density matrix, and therefore they don't contribute to the entanglement entropy. Only the first case does. And so if you just calculate how many pairs have ended up with one pair inside the region A and one pair having flown outside the region A, then we get 1 bit of entanglement entropy for each one of those cases. then we get an expression like this. So T here is what's called the depth of the circuit, the number of time steps we've taken. And what this is showing is that the entanglement entropy increases linearly in T until we get to a time which is set by this size of the system, the linear size of the system, in which case it saturates. So just to actually plot it, this is what it looks like. We have this characteristic ramp type curve with linear growth followed by saturation. Okay, so this is a very common feature in the entanglement entropy. Well, I should say in systems where we have been able to calculate how the dynamics of entanglement entropy. And it's often explained in terms of the causal propagation of some sort of quasi-particle. So the idea being that once all parts of this region are in causal contact with all other parts, the entanglement entropy is saturated. And this picture is originally due to Calabrese and Cardi in 2005. Now, of course, in this example that I was just talking about with swap gates, you can think of the qubits which are sort of flying off to the left and right as kind of non-interacting particles. But what we'll see next time is that this picture remains true in certain circuits where there is no quasi-particle interpretation at all. So although we spend quite a long time thinking of it in terms of this quasi-particle picture, it's probably a lot more general than that. Okay, correlation functions. So this is slightly more general than just thinking about an expectation value. Now we have a correlation between some initial operator at some time 0 at some site 0 and some operator at some later time t at some site x, which has been obtained by evolving in the Heisenberg picture. And we're going to average, when we calculate this correlation function, we're going to average over all states uniformly. People will frequently describe that as the infinite temperature limit, or you should remember that temperature isn't really defined in these systems because we don't have a Hamiltonian, don't have a Boltzmann distribution. But that terminology is often used. Now, how does it look in our graphical representation? It looks like this. So we're now in, the difference from our previous case is only that we, as well as having an operator in the middle here, this sigma alpha, which represents our evolved operator, we also have a sigma beta, which represents the operator at time 0. So if you start now applying this unitarity condition that I talked about earlier, you'll find that just, again, you can cut away great portions of this circuit until you're left with this kind of skeleton circuit, which you see on the right here. Now, if the sigma beta was outside the light cone of sigma alpha, then this process would be complete. You would actually cut away all of the gates, and you would end up with a correlation function which factorized into a product of traces. And if the operators had 0 trace, it would just give you 0. So this says you have 0 correlations outside of the light cone and non-zero correlations inside the light cone. When we're on the light cone, the remaining sort of skeleton that we get is particularly simple. It has this kind of structure here. And now if we sort of start just rewriting this or folding it up in various ways, we can get this kind of structure here. So all I've done is taken that sort of elongated skeleton and folded it up. And this, here you can see the correlation is calculated by propagating something from left to right. Here Q is just the local Hilbert space dimension. So we've been talking about Q equals 2 up till now. And the normalization, you can get it by comparing with the identity. It's not too important. But the key thing about this is that the intelligent way or the efficient way to evaluate it is by iterating, if you like, from left to right. And what exactly you're iterating is a map which maps operators to operators. And that map has the graphical form depicted here. So to calculate a correlation function like this, you iterate this map acting on sigma alpha t times until you get, and then take the trace of the resulting operator with sigma beta. So these are examples of what are called quantum channels, which are completely positive trace preserving maps between spaces of operators. This quantum channel has a particular additional property of being what's called unital, which means it takes the identity operator to the identity operator. But the key thing to make about this is it's very easy to do. Right? You just have to iterate a sort of finite dimensional matrix several times, as many times as you like to go along this light cone. So typical behavior of these correlation functions, bear in mind this is just a general circuit, so meaning a general unitary matrix. They generally have this exponential decay after some initial transient, no matter whether you look at XX, XY, ZZ correlations. We'll see more specific kinds of correlations in the next lecture. The interesting thing is that you can do this at all, right? I mean, it's supposed to be difficult to calculate correlation functions in many body physics. It's famously a sort of ferociously hard challenge. But the point here is we've taken a very particular kind. We've looked, by looking on the light cone, we're essentially looking at something which has got, the appropriate notion is one of Lorentzian distance, right? So the being on the light cone essentially means being at null separation, and that means that the problem is still tractable. In fact, it's still tractable if you begin to take steps inside the light cone. It's just that the size of your quantum channel, becomes a channel which acts on 2 sites or 3 sites as you step inside, and that way it becomes exponentially larger. So generally, to calculate correlations far inside the light cone, it is exponentially hard. Okay, last thing I wanted to talk about in the last couple of minutes is the notion of operator spreading. So the correlation function that we just talked about is only one particular part, if you like, of the operator the operator evolved in time. In general, if I evolve an operator in the Heisenberg picture, I'll be able to express it in terms of products of local Pauli operators and identity operators at each site, together with some coefficients. So I've got, at each site, I've got 4 possible operators I could have, and I've got a general n operator acting on n body sites, n qubits, can be written in terms of all of these coefficients, where these coefficients have some time dependence, and they start off at time 0, localized just on a single Z operator in this case. So you can extract the correlation functions. If you had this expansion, you could extract the correlation functions just by taking a particular component at time t corresponding to having a single Z at the site where you want to evaluate the correlation at time t. But this represents only one part of the expansion. These coefficients obey a normalization when you sum over all of them. They're real, and when they're squared and you sum over all of them, you get a constant. But the thing that I want to just to explain in closing is like a very, very simple example of this kind of operator dynamics. So imagine you've got a gate of the exchange kind that we met already, which parameterized by some theta. And you act on a operator with this kind of gate. And just by multiplying this out, you can see that this is the expression which results. And what we're going to do now is something that we'll use a lot in the next lecture. We're going to use an ensemble of random gates. And in this case, we've just got a single parameter. So a very simple ensemble. We're going to take a distribution of these parameters theta, it's going to be plus or minus theta 0, but with some bias delta. And if we perform that average, then we get this expression here. So the interpretation of this expression is that the first 2 terms represent the possibility of the operator just switching sites because it's been swapped. And the last term represents actually sort of a true kind of quantum dynamics, which is due to the asymmetry, the fact that the J tends to have a positive sign or a negative sign predominantly. And this allows us to really controllably understand this kind of operator dynamic. So in the continuous time limit, this equation has this form. It doesn't matter too much. If you calculate the commutator that's represented, that appears in the first term here, what you can see is that operators tend to split. So in other words, if I have a non-identity operator on a site, it can split into 2 non-identity operators. Oh, my time is up. Or they can merge and form 1 operator. So I'll just finish this picture and then close this lecture. So in the J equals 0 limit, this describes a very simple process of diffusion of single operators. Okay, so I can take the operator number of non-identity operator. If I've got one non-identity operator, it's not coupled to two non-identity operators. It's not coupled to three non-identity operators, and all of them just diffuse in a simple way. But if I take J to be non-zero, then these operators, a single operator can split. So an X can split into a Y and a Z, and a Y and Z can likewise reform. And you get a kind of picture in perturbation theory like this. Now you can develop the perturbation theory, but the key point that I want to get across is that when you turn on this non-zero J, the operators tend to spread out and go from occupying one site, occupying many sites. And so this is a generic feature of operator dynamics, which goes by the name of operator spreading. And what we did here was to basically play a kind of trick. We made things simple by averaging over the operators, right? By averaging over the circuits. At J equals 0, remember that's where there was symmetry between plus theta and minus theta. Averaging meant that many of the coefficients in the operator expansion vanished because they've actually got signs, and the real numbers, they've got signs, and they average out to 0, leaving only these very simple coefficients which describe operator diffusion. If we allow J to be non-zero, which means we've got a tendency to have, say, plus theta over minus theta, some contribution survives, and we can actually do perturbation theory calculations. But in general, if you take a single circuit with some single concrete realization, one operator is going to grow to be some enormous complicated object. And so to understand that object, we'd like a measure in particular which doesn't care about these random signs which appear in the expansion. And that's something that's called the out-of-time order correlator, and we'll introduce that next time. Okay, so next time I'll start off by telling you about this out-of-time order correlator, and then we'll look at some particular kinds of quantum circuits where you can calculate it in more or less exactly. All right, thank you.
All right, thank you, Austen. Any questions from everyone? Anyone?
Just trying to understand this. So you had this picture of like the growth of entanglement between two parts, which grows linearly and then saturates. And for the so you had initially you had pairs of these entangled pairs, and then you did the swaps, and somehow it looked like the entanglement is spreads. So it looks like the entanglement between two parts is kind of a sum of entanglement between pairs. That's the kind of picture.
Yeah.
But is that?
It's not generic. No, that's just particular to that example. So in general, you can't have such a simple picture, but there are still situations where the entanglement grows exactly as quickly, but for slightly more complicated reasons, which we'll see next time. Okay. So, but it's not decomposed in general as a sum of the entanglements due to Bell pairs.
Okay, and in the other picture that one has in terms of quasi-particles, that also is quite a kind of similar. But you said that
yes,
it's different from this in some sense.
No, I would say it's morally quite similar to this swap situation in the sense that you really do the entanglement really is you have sort of essentially quasi-particle pairs which are produced in a sort of pairwise entangled state, and it arises like that. But again, it's not really the generic way in which this entanglement growth happens, which we'll see next time.
Hi. You talked about Lorentz invariance because of this propagation along the light. Is it possible to think of conformal field? I mean, is there some discretized these in terms of these?
So you want conformal invariance as well?
Yeah.
Okay. So
I mean, this dual unitary set.
Yeah. Okay. So you. Okay. So there are two things. So firstly, the existence of the light cone suggests that there is something analogous to Lorentz invariance. And indeed, it's not too difficult to figure out what the discrete kind of Lorentz invariance is in these systems. And I could draw it for you afterwards, but essentially the point is, if you think about what Lorentz transformations look like in light cone coordinates, they're just a squash in one direction and a stretch in the other direction. And so basically what that means in this circuit, if you turn these circuits by 45 degrees, and they're made of a sort of square lattice, and you are free to chop that square lattice up into rectangular blocks of any size you like, and it still represents the same dynamics. That's Lorentz invariance, right? Discrete Lorentz invariance, essentially. And then the question is, like, can you go further and add conformal invariance? I think your colleague Luis Manzanares has a paper where he's sort of proposing a particular kind of transformation. And yeah, I mean, I'm not totally convinced that that's the only way of doing it. So, but I suspect there may be some, at least for some kind of gates, places where ways you could implement discrete conformal invariance as well. It's different from the kind of discrete conformal invariance which people have considered, if you like, in the lattice setting up till now, because it's Lorentzian rather than Euclidean, right? They're different symmetries. So. But it's an interesting idea or question, I think.
Yes.
Is that better? Okay, fine. So when you talked about computing the correlations on the light cone, it reminded me a little bit when you're kind of computing correlation functions in scalar field theory. You very often boost to a particular frame, compute the correlator, and then boost back. Can you actually exploit an effective Lorentz transformation to kind of explore other areas where it might be difficult to compute directly?
I don't know, actually. That's a very good question. Yeah, maybe you'd have to tell me exactly what you mean for the relativistic case, but maybe. Yeah. Although, I mean, the only thing that would hesitate to say, because it would give you a kind of free lunch, because this Lorentz invariance is always there for any kind of unitary circuit, and I would be surprised if you could get anything for free like inside the light cone. But maybe it's something for some kind of special class. Yeah.
Okay. Any more questions? One more.
So I was just curious. So when you compute operator expectation value or operator evolution equations in general, part of the trouble comes from non-commutative, from the non-closure of the algebra, right? So if you have a closed algebra, more or less you can handle things, and these are the cases where we can. So is there any diagrammatic insight that on with respect to operator spreading, that we can gain for these kinds of situations? Because the representation that you've presented in terms of poly letters, this is of course used for, in LCU and block encoding. I mean, it's all over the place in quantum circuits. So. So I was just wondering if there is any diagrammatic insight that we could get from this, the diffusion part of your.
Yeah, so in the paper that I was referring to, there's a paper by Peter Kleiss and I from last year. We do diagrammatics. So we use this trick. So essentially by using this average, it's a way of making the commutator part small relative to the diffusion, and then you can, it then maps onto the problem of quantum field theory with a particular cubic vertex. And then we did basically Born approximations, so just the one loop calculation to understand how diffusion was renormalized. So that's kind of like, and so depending on how much appetite you've got for calculating diagrams, you can then go and do whatever you want with that formalism, but we did the simplest thing. So.
Okay, great. Yeah, let's thank Austen one more time for this very interesting lecture. And we will break for coffee. We'll come back at 11:30.